Okay, so on Friday we started section 7.4, and what we were talking about are real world problems where you have exponential change. And to start off the section, we talked about how exponential change, exponential growth and decay, how that can come into a real world problem. And this is the simple idea that leads to kind of some complicated math. When a quantity changes at a rate proportional to its size, so things like populations and radioactive elements, then what happens is you actually have this mathematical equation that relates the rate of change of your quantity, so the derivative, with the original quantity, and it's proportional, which means it's a constant multiple. So we aren't going to work through these details again, but you might remember that we ended up solving a differential equation. And let's see, so you have these in your notes already. Okay. And then on the next page, the back of this page, I have this written out neatly. So this is the formula for exponential growth or decay. And since that's not on this page, I should remind you that y with a little zero next to it, is the initial value of your quantity. So it's like your starting population or something similar. And k was the growth rate from the formula that we started out with, the proportionality formula. So k is the constant of proportionality. Okay, so that's the math behind what we're doing. And then last time we went on to talk about the growth of a population. We looked at a bacteria culture, since they grow pretty fast. And the growth rate k represents something like the fertility rate minus the death rate. So this would be the number of new bacteria in our example, and then you subtract off the number of dead bacteria. And that's where the k comes from. But the math, we don't really have to worry about that too much, of course, since we're just dealing with formulas. Oh, and this answer, which I never actually wrote down because we went to a calculator, was approximately 4.92 times 10 to the 41 power, which is a huge number of bacteria. But we're moving on today to this idea of radioactive decay. So decay is the opposite of growth. Our quantity is going to be getting smaller. And in this particular example with radioactive elements, we're looking at radioactive decay. And if you haven't been in a physics class for a while, radioactive decay is where an atom breaks down into its constituent parts and it emits matter and energy. So radioactive decay is related to, well, you might have heard of things like uranium and plutonium and those kinds of dangerous elements. That's what this has to do with. And the idea, the way that radioactive decay works, is that it occurs at a rate that is proportional to the quantity of the element that you actually have. So over a given amount of time, a certain quantity of your element is going to decay, to put it a different way. Let's say a certain proportion of the atoms will decay. Okay, and like I said, relating to the bacteria example, this is a math class, so we're not going to be worried uh, too much about the actual science of what's going on. If we wanted to do that, we'd have to talk about things like quantum mechanics and stuff. We're just going to focus on the decay itself. And before we move on, I need to add a little bit more down here. So the way that we are going to write radioactive decay is ever so slightly different than what we've been doing. And that's because what I want to do is consider this as my original formula. That should be a y. So we want to start with this. And you might remember in the original formula, we just had a k. And when we're talking about radioactive decay, usually we put an extra minus sign on here. And what we think of is k is positive. But since we put this extra minus sign on here, we're saying that the population, the amount of radioactive element that we have is going down, has a negative slope. So this isn't a huge change, but it does lead to a minus sign in the exponent of our exponential change formula as well. So just make sure you remember that there's going to be a minus sign because we're talking about decrease. So a negative slope means your function is decreasing. And that's why we get a negative up there in the exponent as well. And there's another idea for radioactive decay. So usually instead of the number k, the actual decay rate, usually what you're given is actually something called the half-life. So instead of the actual rate, the half-life is of your element is the time that's expected to pass before half of the element in your sample decay. Let's see, I'll use the word nuclei for the individual atoms, the pieces of your sample. So you might remember from a science class that a nucleus of an atom is basically its center. Okay, so let's look a little bit at the math of a half-life, and it relates to the initial value. So the half-life tells you how long it takes for your amount, your y0, to decay by half. So after one half-life, you're left with half of the initial value, the initial quantity of your element. So of course, that's just 1/2 times y0. So the question that we want to be able to answer before we get into any concrete examples is, how is this half-life, this idea that's usually used in physics, how is it related to that decay rate k in our formula? And in order to figure out this relationship, what we want to do is look at the formula. We want to plug in this, the 1/2 y0, into our formula. So I'll write the original formula over here. So this is just the quantity left after a given amount of time, the old exponential decay formula. And what I want to do is figure out how to relate half-life and k. And in order to do that, I'll plug in a half y0, a half of the initial value, on the left-hand side of the formula and try to solve for the amount of time that goes by before half is left. So plug in y equals 1/2 y0 and solve for y. Excuse me, solving for t. So once I do this little bit of algebra, it'll tell me the solution, the amount of time that went by, in order for half to be left, or half to actually have decayed, depending on which perspective you want to take. So the goal is to eventually get this t out of the exponent. But before I can do that, I need to move this initial value, y0, to the other side so that I can take the natural log. So when you divide through, both of those cancel off on the left and the right side. And so this formula simplifies, actually. It's just 1/2 is equal to e to the minus kt power. And now we can take the natural log of both sides. because remember, the natural logarithm is the inverse of the exponential function. So it cancels, essentially. Let's come back over here. So the natural log of 1/2 is equal to minus kt. So we've gotten rid of our exponential function. There's only a little bit of work left to do. Before I move my constant over to the left, though, I want to take a look at this natural log of 1/2. When we're dealing with natural logs, we don't really like to have fractions inside of them. What we'd prefer to do is to rewrite this fraction with a negative exponent and then move that exponent to the front. And that helps us simplify just a little bit. So what I mean is 1/2 is really, or at least another way to think about it, is really 2 to the minus 1 power. So remember, the minus 1 tells us to flip the 2 to the bottom of our fraction, to take the reciprocal. And what I want to do is pull this negative exponent out to the front. And what we're left with is minus 1, so we don't have to write the 1. So minus natural log of 2. Are there any questions about how that works? How we can go from here to negative log of 2? Okay, so what this does is it lets me get rid of my minus signs. So if you multiply through by minus 1 or divide by minus 1, those negative signs will go away. And then you can finish off by dividing through by k to solve for t. And you get this simple little formula. So the half-life is actually just the natural log of 2 divided by the decay rate. So even though the half-life seemed maybe a little bit complicated when we first started writing things down, there's actually this simple formula. This is what you should remember. Any questions so far? Okay. So next, I want to move on to an actual example, a word problem. And I wrote down most of it. The number of atoms after T days in a sample of polonium-210 that starts with Y0 atoms is given by this formula. So I'm just going to give it to you in this particular example. Okay, so this is it. And we can read off the decay rate from the exponent up here, and Y0 is the initial value. And I wrote this down for any initial value because the question here is about the half-life and not necessarily about the amount that's actually left. Because half-lives have to do with proportions, so the actual quantity isn't as important. So like I said, this in the exponent, this minus 5 times 10 to the negative 3, this is k, the decay rate. Or really, if I include the negative sign, this is minus k. So k, we would drop the minus sign. This is that little detail that I wanted to be clear about up front a few minutes ago. So k is actually just 5 times 10 to the minus 3. And remember, we're finding the half-life, and just a second ago, we found a formula that relates the half-life T with the decay rate K. So instead of going back to the algebra of solving, we can just plug K into the formula. So T is equal to log 2 over K. This is our formula. And all we have to do is plug in the value. So this is something you would probably put in your calculator because, well, we can't really do natural logarithms by hand, or at least not very easily. So I should really use an approximate sign here, not an equal sign. And this would come out to about 139. And if we go back up to the problem, we'll remember that t was in days. So this is 139 days. Any questions over the example? Oh, okay, so if you're curious about any of these topics that we're talking about, since they are related to science and other things, like this one, polonium 210, if you wanted to take a look at its Wikipedia article, which I have pulled up here, you can read a little bit about the actual science of how it works and its history. Like this one, polonium 210 was identified by Marie and Pierre Curie over 100 years ago. And this particular element has what would you call this? A sordid recent history. If you look at that highlighted text there, there's been a couple cases, at least one in recent history, where this element has been used to poison people. And the reason why this particular element is dangerous, why it could have been used to poison people, is related to this half-life of 139 days. This is actually an extremely short half-life, at least in relative terms, compared to things like plutonium and uranium. Which you can also look up. But these are the two that you might be more familiar with. So both of plutonium I think has a half-life of a few decades, and uranium, I think its half-life is in the order of 1 billion years or so. Um, so 139 days compared to these two is extremely fast. So what that means is that this particular element, polonium-210, it's emitting a lot of energy and a lot of particles whenever it decays over a really short amount of time. Any questions over that example? I think I might have already asked. Okay, so let's do another one here to wrap up this section. So in this problem, we're going to look at carbon-14, which you might know from carbon dating. Maybe I'll just write that word down. So carbon dating is a process that's used by, I guess, like archaeologists and other similar scientists to figure out the age of artifacts. And in this example, we're actually going to do a little bit of the math that is behind carbon dating. So let's just read it. The half-life of carbon-14 is approximately 5,730 years. If 20% of the carbon-14 nuclei of a sample have decayed, then what is the age of the sample? So if you're wondering a little bit about what I mean here, is things that are living, that are growing, build like their bodies and such, like you could imagine like a tree trunk or even your own body, and a certain proportion of the carbon-14 in nature is constant. So if you can tell the proportion of your sample compared to that constant proportion, then you can do this carbon dating process. And that's a very loose description of how carbon dating works. So that's another topic that you can look up if you're curious. So in this particular sample, 20% have decayed. So if 20% have decayed, how much is left? How much of the carbon-14 is left in our sample? Anyone? And remember, we're just talking about as a proportion of the total. Please don't talk over each other in your rush to answer.
It's just 80%.
It's 80%, right? So 80% of the initial value. So if we're looking at our decay formula, the y equals y naught times e to the minus kt power. So remember, y represents the current amount. So if we're going to solve for the amount of time, we have to figure out how long it takes, t, for there to be 80% of our initial value to remain. So we're going to plug in 80% of y0, the initial value. But proportions are the important thing here. We don't have a concrete number for y0. How can we get 80% of an unknown number? What should I actually write on the left-hand side?
4/5.
4/5, good. So 80% corresponds to the fraction 4/5. If you want to make it a little bit easier so that you don't have to think of fractions, you could convert your percent to a decimal, which is essentially what you've done. But if you want to write it as a decimal, you can write 0.8 y0. So fraction or decimal. I'd recommend sticking to decimals because you are going to plug numbers into a calculator at some point when you're solving these things. So I'm going to use this one. Decimals are generally just a little easier when it comes to calculators. So I'm putting this in on the left side for the current amount. So I'm saying 80% of the original amount remains. And I want to solve for t. Does anyone notice a problem? This is what we want to solve. Does anyone notice a problem with this? Can we solve it yet? Are there perhaps some missing values?
We don't know k.
Right. So the y0 we don't have to worry about because when we start simplifying, this will cancel off both sides. So the initial value doesn't matter. What does matter is k, the decay rate. So we have to find k first. And in order to find k, we're going to go back up to the problem statement and look at the half-life here. 5,730 years. And we're going to take that number and use our formula for the half-life. We know what t is in the half-life. We know it's 5,730. And we're going to use that to solve for k. Okay, so let's come off over here on the side. We know that t is equal to log 2 over k, where t in this particular case is the half-life. Sometimes there's a special symbol for half-life, but we're not going to worry about it. Lambda, the Greek character, I think is usually used. But we're going to use this formula to solve for k. We're going to plug in our known half-life Okay, so then you'll rearrange this formula, multiply through by k, divide by 5,730, and you'll see that k is equal to log 2 over the half-life. And you can just leave it like this when you plug it in the formula, which is usually a good idea. or you could enter this in a calculator and get a decimal approximation. It's about 0.000121. It's a really tiny number. Let's see, running out of room here on the right. But you could rewrite this as 1.21 times 10 to the minus 4 if you wanted to use scientific notation. Remember, 10 to the minus 4 tells you that you should move the decimal place 4 times to the left from here to get back to this. Okay, so this was a separate calculation that we needed. Box that in maybe off to the side to keep things organized. And we'll plug it in here so that we can solve for the amount of time t that's gone by for 20% to decay. Okay. Okay, so now we have to solve. And like I said, the initial value y0 doesn't really play a role here because it just cancels off. But we will have to use the natural logarithm to get rid of the e, to get rid of the exponent, or excuse me, we're not getting rid of the exponent, we're getting rid of the exponential function. I have to be careful with the way we say that. These go away. Okay, so what's left on the right is just that decay rate that we found, minus 1.21 times 10 to the minus 4, and t. So to finish off, to actually solve for t, all we have to do is divide through. Okay, so at this point, you might be a little worried about the minus sign down here, because we're talking about a length of time. We know this is going to be positive, but for some reason I have a minus sign down here. But this is actually going to disappear because this natural logarithm of 0.8 is actually negative. Something to keep in mind about logarithms is that logarithms can be negative when you have numbers smaller than 1 inside of them. Okay, so at this point, you would plug it into a calculator. Just put a note here. Use your calculator. Maybe we'll take a look at Desmos in just a second. But once you enter it, you'll get this number, 1,844. And I've just rounded it to the nearest year. So our sample where 20% of the carbon-14 had decayed is this many years old. It's 1,844 years old. And that's the way that carbon dating works. So an archaeologist figures out how much of the carbon-14 is left, and then does this calculation to figure out the age of the artifact.
So why'd you put the negative there again? Like the in front of 0.8?
Here, I'm not pointing to 0.8. I'm pointing to the whole natural logarithm. What I wanted to point out was that natural logarithms can be negative. And it's actually going, the minus sign here is going to cancel this minus sign in the denominator.
Okay, got it.
Yeah. Okay, and with the last few minutes of class, I think it would be a good idea to go look at some graphs. Switch back over to my browser. Go to Desmos. And we'll put in, let's see, I think you can still see my camera. We're going to put in the formula with our decay rate K. And that's still misbehaving. Let's see if this does it. No. That should help. Yes. Okay, so what I did was I added a slider for y0, the initial amount. And if we change this, we'll have to zoom out pretty far in order to see anything interesting, because you might remember it, the half-life is over 5,000 years. That means in order to see anything interesting, we should have something on the scale of maybe 20,000 on our y-axis, which would be 4 half-lives, approximately. And let's change the y0 value to be, let's just pick the number 6. And adjust the scale. There we go. Now we can see something. Okay, so I just picked some number y0, and I picked 6, and we can look to see where we get 80% of 6, and maybe let's pick 5, since 80% of 5 is 4. We can see where it crosses the line for 4. Let's see, we'll have to be a little bit careful. It's not going to let me show you the exact point, but we can see that it's right in that range where we found. So when our function value is 4.002, the x value is 1,840. So if it went down just a little bit further, we can see it would be correct. But we can't get that much detail here on the graph. Okay, so what if I changed it to another number? Let's go all the way up to 10. And remember what I said, it's the proportion that matters, not the initial value. So you might think since we start with more, it's going to take longer to decay by 20%, but actually it doesn't. 20% of 10 is 8. So we have to figure out where our function is equal to 8. And again, you can see it's exactly the same. And if I change it again, let's see, what's another convenient number? Let's just go with something low, like 1. 80% of 1 is 0.8. That's in here. And you can see again, it's the same amount of time to decay by 20%. So I just wanted to point that out on the graph. Remember, we're talking about proportions when we're doing things with exponential functions. Most of the time, we're talking about proportions. Does anyone have questions at the end of class here?